Chapter 4 continues with our idea of dealing with our measurements, our quantitative measurements, and how we might get more information out of them. So Chapter 4 is all about statistics. So let's think about how this might come up as a problem. So let's say that we measure the lead content in drinking water. So there's really no acceptably safe level of lead in drinking water. But we still might want to know what it is. And if it gets exceptionally high, then certainly that's a big problem for a community. So let's say we get a sample of drinking water and we measure the lead content and we get a number 19.5 parts per billion. Well, so how do we know if that measurement is correct? So maybe we made a mistake in the procedure. How would we know that? What could we do to increase our confidence in that measurement, right? Well, one easy thing that we might do is if we have a big jug of this water sample and we took a small part to do the analysis, let's just take that same jug, get another little part, and repeat the analysis, right? If we get the same number, that either convinces us that maybe we didn't make a mistake, right? Because maybe we've learned how to do the procedure correctly. Maybe we've learned how to do it wrong. That would be a systematic error, but at least it gives us a little bit more confidence. So that's what we do is we measure the lead content of the sample several times, right? And so we get all of these numbers. So here's our 19.5 first number, but we also get these other numbers, right? Now they're all kind of close, but they're not all the same. So why aren't all the numbers the same? Well, that goes back to the topic that we talked about in Chapter 3, right? They're not the same because of random error, right? Hopefully we've eliminated the systematic error in our method that we know how to do it right and correctly, but there's going to be some variation, right? Maybe we're using an electrode, and so there are little fluctuations in the electrical current because of static electric fields and temperature. Maybe there's just a little bit of variation every time we pipette our sample, right? So all of these little random factors contribute to make the value sometimes a little bit higher, sometimes a little bit lower than what the true value might be. So we know now why all these values maybe aren't the same, and that's due to random error. But which one of these values should I take as the correct value? So if I'm trying to report, well, what is the lead content in this sample? Which number should I use? Well, there's no good reason to pick one number over the other, right? We use the same measurement. So what we really need is some number that kind of represents this whole data set. What is the typical value of this whole data set? Right? And when we do that, we are actually using statistics. Now, you guys know what that value would be. That would be the average, or the mean value is probably the best representation of the typical value of this data set, right? But that number is a statistic. So a statistic is any number, so it will always be a number, that is used to represent some property of a data set, or perhaps a comparison between several data sets. So we get numbers that help us understand properties of the data set. Some have an even more broad definition of statistics, saying that statistics is the science of data, or the science of data processing. So those are interesting things. But anyway, here's our definition for the average or the mean. So it turns out that if you have repeated measurements and there's just random error, they're going to tend to cluster around a central value. That's called the central tendency property. And so we can get an estimate of what that central tendency is, what that typical value is, by taking the mean value. Sometimes it's called the average value, but average can mean different things. So sometimes we use this word mean as a better number. And so we know how to do that. We add up all the numbers and we divide by the number that we added together to get the average, right? This is how we have learned to calculate averages. So we come up with an average of 19.4. In terms of a fancy math formula, here it is for calculating the average value. So X is our measured property. The over bar is just our symbol for the average. So the average value of X is equal to what? Well, this capital Greek letter right here, sigma, means take the sum. And a sum is going to have an index I. We're going to start it at 1, and we're going to go up to n. N is the number of data points in our data set. So X sub I, right, the first index would be I equals 1. So we're going to have I sub 1, and then the next one would be I sub 2. So I sub 1 plus I sub 2 plus I sub 3 plus I sub 4, and so on up to X sub I, x with I equals n, so x sub n. Okay, so that's kind of what that means. So this number right here, we could call that x subscript 1. The second number would be x subscript 2. And we would go up to x subscript 5, which is the 19.7 data point. And we just divide by n the number of data points. We will most often be doing our calculations in Excel, so this is the formula that you could type into Excel to calculate an average value. So we always start a formula with equals, then we're going to use the word average, and then in parentheses we need to select the cells that have the data points that we want to average. Now usually we will list those in kind of a range, maybe down a column like this, and so we want to start with cell B2. The colon means all the cells in between cell B2 and B6. So we're going to start at cell B2, run through cell B6, and do this operation. So calculate the average using those values. And so that is a statistic and a way we might calculate the statistics. So another question that we might want to answer about our data set, well, we see that the numbers are not all the same, but how much spread is there in the data set, right? How scattered are the data points? We know that that scattering is due to random error, so this is kind of a question about how big is the random error in this set of measurements. So one way that we might calculate the spread is to calculate a number called the range, right? So the range is just the difference between the largest and the smallest values in your data set. And so it measures a spread or a scatter, you know, how far apart are the data points typically, but it tends to overestimate typical spread if there are outliers. So there may be a set of random errors where you get pretty far away from what the true value is. And if you have that in your data set, it's going to give you sort of an overestimate for what the range is. So a better definition for a range, the typical range in measurements, the typical scatter in your data, is this property called standard deviation. Okay, standard deviation. And this is a good, robust measure of the typical spread in a data set. How scattered are the data points? And this will be our usual measure for the precision in a set of measurements. So how reproducible are they? So the smaller this number, the smaller the standard deviation, the higher our precision will be. So first off, we're going to define the deviation from the mean. So D for deviation, and it's going to be the deviation of a particular data point I. So we've got a bunch of data points, 1, 2, 3, 4, and so this would be for data point, I, data point 2, whatever. And so what we're going to do is take that data point and subtract from it the mean value, right? So if the data point is bigger than the mean value, we're going to get a positive number. If it's less than the mean value, we'll get a negative number. So deviations can be positive or negative, depending on whether they're higher or lower than the mean value. And so the way we define the sample standard deviation, so it's a little bit like a mean deviation or an average deviation. We're kind of going to average these over the data set. So you see there's this sum here. The problem why we can't do an exact average is that because some of these numbers are positive and some are negative, they would tend to cancel each other out. So in order to make all the numbers positive, what we do is we square the deviations, right? So each deviation is going to get squared. That's going to make them all positive because we know when you square a negative number, you get a positive number. And then we're going to add them all up, just like we did for the average. But instead of dividing by the number of samples, we're going to divide by something called the degrees of freedom. So this denominator here is called the number of degrees of freedom. And it's the number of data points we have minus the number of things that we have calculated from those data points. So each deviation, right, we're using a mean value that we calculated from our data points. So that's why we have to reduce the degrees of freedom by 1. So just remember that we're dividing by n minus 1 here, but it's still kind of like an average, right? Then we have to undo the squaring bit that we did because now the deviations are going to be, the square of what they are, and we want to make them the correct size. So that's why we take the square root of that whole stuff inside at the end. But it still kind of looks like an average. Here's another way of writing it in terms of the individual data points. So you're going to need to calculate an average value, and then you need to do this for each data point. So you have to do a subtraction, then you have to square them, then you have to add them, then you have to divide by n minus 1, then you have to take the square root. So it's a lot of calculating. By hand, this can be pretty tedious. So luckily for us, There are formulas in Excel that can do this. There are also functions on your calculator that can do this. So read in your calculator manual, look it up online, and figure out how to calculate summary statistics on your calculator. So that will calculate for a set of data the mean value, the standard deviation, and a couple of other things that we won't talk about quite as much. In Excel, though, the formula is the equal sign, and then you want to type stdev for standard dev, a period, and then S. So stdev.s. So the S stands for sample standard deviation, because there are other kinds of definitions for standard deviation. And then you just select the range of cells that has the data points in it, and it will spit out the standard deviation. So for us, the standard deviation, the typical spread in our measured values for the lead concentration was 0.53 parts per billion. So that's a typical spread. So they differ by each other by, typically plus or minus 0.53. And so that might be our estimate of the uncertainty in our lead measurement. So sometimes, just like we talked about relative uncertainty, sometimes it's useful to talk about relative standard deviation. So we take the standard deviation and we divide it by the average. So how much spread is there in comparison to the average value? So we just form this ratio. And of course, we can make it a percentage by multiplying by 100. So RSD for relative standard deviation, or percent RSD for percent relative standard deviation. This is useful if you want to compare spreads in measurements with different units or scales. So maybe you're measuring the spread in measuring the mass of pennies and the spread in measuring the mass of elephants, right? So those are very different scales. So you might want to use percent RSD to compare your precision in those two different kinds of measurements. Or perhaps you're comparing measurements of grams to measurements of milliliters, right? How do those precisions compare? Again, they're different units, so you can't compare their absolute standard deviations. So we use relative standard deviation to do that. Again, measurements with the smallest percent RSD will tend to have the highest precision, the highest reproducibility. So this is a great way to compare precisions of different measurement. So when we report an uncertainty in a mean value, we usually do it as the standard deviation. So like with our lead data, we're going to report to people, well, here's what we think the typical value of lead is. It's going to be the average. What's our uncertainty? Well, it's going to be plus or minus the standard deviation, right? So that 0.53 that we calculated over here. So that's how much we think our numbers might vary from this. So the true value, we're hoping there's a good chance that the true value is within 0.53 of the average value. So 0.5, actually, we're just going to round that to one decimal place. So we're going to report the answer is 19.4 plus or minus 0.5. So we're telling people, hey, there's a really good chance that the actual lead concentration in the sample is 19.4. There's a really good chance that it's within 0.5 parts per billion of that number. We also usually report the number of trials here, so n equals some number. In our case, we did 5 trials, so we'll report that. That way people know how many data points were in the average in standard deviation when you report it. So I mentioned here that we stand a really good chance that the true value is in here. Well, somebody might ask, well, what chance, right? What is the chance? Are you 50% certain that the true value is within 0.5 of 19.4? Or is there a 99.999% chance that that's true? I mean, I want to know. Give me a number, right? You're just telling me, a pretty good chance. What does that mean, right? We want to quantify that. So how do we go about doing that? Well, it turns out we know something about the way that random error kind of spreads out and how far away it can move you from the true value. And it turns out that random error follows something that we call the Gaussian distribution. This is also sometimes called the normal distribution or the normal error curve. And this is a way of representing the chances of making a particular measurement due to random error. So measurements differ from each other because random error. Typical random error in chemical measurements leads to a distribution of values. So how likely are you to measure something? So let's look at this plot. This is a plot of the Gaussian distribution. So the true value is right here at the peak, okay? And here's our mean value. So if we take enough measurements, the mean value will equal the true value. Okay. So the height of this peak is the probability that we measure that value. So it is most likely that we're going to measure the true value, the mean value. But there's also a pretty good chance that we could be a little bit off from that due to random error. There's a much lower chance, because this curve is much lower, that we would measure a value that is far away from the mean value due to just random error. So this is sort of telling us something about chance. So that's summarized here. The mean value corresponds to the peak. If there is only random error, then the mean value or peak value will equal the true value. But in order to do that, you must make an infinite number of measurements. So what I mean by that is, if we make a measurement and make sort of a bar graph, right? So we make a whole bunch of measurements and we make a bar graph. Then the more and more measurements we make, the more and more the bar graph is going to look like this curve. And if we make the bends in our bar graph, the thickness of our bars smaller and smaller, and take an infinite number of measurements, then if there's only random error, that bar graph will exactly fall on top of this curve that's predicted from the mathematics of our situation. So that's kind of cool. So the mean value is certain to equal the true value if we do an infinite number of measurements and if there is no systematic error. So this is just random error, okay? So the y-axis here, the height of this curve, is giving the probability of measuring a certain value. So here's an x value right here. What's the chance that I would measure that? Well, it's here. Whatever that number is, that's the probability that I would measure that value. So the area underneath this curve then tells you something about the probability of measuring a range of values. So you see out here at about half the height of the peak, not quite, it's a little bit less than half height, or a little bit more depending on where you're measuring from. This is that value that we're going to call 1 unit away from the standard deviation, and that's in units of this parameter that we're going to call sigma. So this little letter here that looks like an O but with a flag sticking off of it, that's the lowercase Greek letter sigma. So if you were within 1 sigma, right, of this central value, so we're talking about the area in between these two lines, what's the probability that you would measure values that are within these two values? Well, we can figure out the area under that curve, and then we know that probability. So here is the mathematical function that describes this curve. So the y value here is this y, and the x value is along this curve. So x is then the measured value. This Greek letter right here is the Greek letter mu, right? We've seen that with micro. That's the true value for our measured quantity. And this sigma here is telling you something about how spread out this curve is, how wide it is. Some people call this a bell curve because it looks like a bell, and this is sort of telling us about how wide the flare of the bell is. All right, so this function involves the exponential function. So e right here is this special number. It's an irrational number like pi. It's called Euler's number, and it's the base of the natural logarithm, and it equals this. So like pi, it's a decimal that just keeps on going and never repeats and never terminates. So that's Euler's number. Mu, again, is the true value. The sigma here is called the population standard deviation. We call it the population because we've done an infinite number of measurements to get this curve. So we have a data set that has an infinite number of measurements. We call that the whole population. And so sigma is called the population standard deviation. So by looking at the area underneath this curve, we can figure out the percentage chance that you are within a certain distance of the true value. So 68.2% of all measured values lie within 1 standard deviation of the peak here, the true value. 95.5% of all measured values lie within 2 standard deviations of this central value. So that's how we're able to say something about probability. So if I say that I know a good estimate for what the standard deviation is, then I can report my measured value as plus or minus that standard deviation. Then I can tell people, well, there's a 68.2% chance that the true value is in there somewhere, right? Because there's a chance I could have measured something out here. But that gives us a way of expressing percentage chances. So the Gaussian distribution helps us now talk about probabilities and percent chances. So standard deviation S, the sample standard deviation, sort of measures the uncertainty in a set of measurements. But what is the sort of standard deviation in a mean value? So if we have a mean value and we were to measure a whole bunch of sets and calculate the mean values of each of those, what would be the standard deviation in those mean values? Well, this is the typical value that we want to report, and it's called standard deviation of the mean. Also sometimes called the standard error. And it's given this symbol, sigma, with a little subscript n, so n is the number of measurements. And it's a measurement of the uncertainty in the mean of n measurements. And it's defined this way. It's the standard deviation divided by the square root of the number of measurements. In lowercase n, here's the number of measurements. And so this makes sense, right? If you calculate a mean value by averaging 3 numbers, you're less certain about that mean value than you are if you were to measure 100 values and average those, right? Then you're pretty confident that that mean value is going to be a good representation of the true value. So the more measurements you make, the more confident you get in the mean value. And so this represents that, because as n gets bigger, right, our uncertainty gets smaller. So there's this inverse relationship. More measurements, better certainty. So our uncertainty decreases by a factor of 2 by making 4 times as many measurements. So let's say you average 3 numbers, right? And you think your uncertainty, your standard deviation, is too large. So how could you improve that? Well, one thing that you could do without trying to increase the precision of your measurements is simply take more of them, right? So if you take 4 times as many, so 4 times 3 would be 12. So if you do a total of 12 measurements and then average those, you will have cut your uncertainty in half. So it might go down from, plus or minus 0.02 to plus or minus 0.01, right? Simply by doing more measurements. We can cut our precision by a factor of 10, make it go down 10 less, by doing 100 times as many measurements. Well, that's really painful to do unless we have an instrument that is automated. So we have instruments with rapid data acquisition. They let us average many experiments in a short time, and we can improve the precision in our measurements simply by taking more of them in a short time. That's difficult to do if you're having to do titrations over and over. 100 titrations is not a fun. So that's a little introduction to statistics. So our standard deviation in the mean will be our typical way of reporting an uncertainty in a mean value, at least until we learn about something called confidence intervals.